So from the last video, I'm sure you're wondering this question. Is Prim's algorithm correct? That is, there's this greedy algorithm of going uh, edge by edge, only taking the cheapest edge at every time step, always going to compute the minimum spanning tree of the graph. And most of all, this question should also wonder you. I mean, when you're choosing the initial vertex randomly, so if in a graph, in a very big graph, you choose one vertex that this one, but on another run you're choosing this vertex, and you let the algorithm play its course, and even then the algorithm will always compute the one MST, the one minimum spanning tree, which is supposedly the correct minimum spanning tree. So is this true? How do we prove that this greedy algorithm is correct? Is Prim's algorithm correct? So the correctness of Prim algorithm, we are going to prove in two parts. Part number one, that at least Prim's computes a spanning tree T star, let's say. So at least it computes a spanning tree. Then part two of the proof will be that this particular T star is a MST, minimum spanning tree. So let's go in part one, and also later we'll look at the running time of this algorithm, and we're going to prove that this is O of m log n, where n is the number of vertices and m is the number of edges. All right. So let's look at this. So part one. This is what we are wondering now. Part one. My claim is that Prim's algorithm computes a spanning tree. Computes a spanning tree ST. So let's define something. Let's define a cut. A cut of a graph VE, vertices and edges. This is the graph. A cut of this graph is a partition of V into two non-empty sets. For example, um, just take any random graph and you cut it into two parts. This like this. This is for one side of the graph and this is the other side of the graph. This is our graph, total graph, and we're just putting a line through it graph arbitrarily, and whatever that line goes through is I mean when we are partitioning some vertex in left side and some vertex is in right side, this is going to be a cut. Okay. So if you have any graph, for example, this particular graph, and I take this line cutting the graph, this is also a cut. Let's say this. So all of the vertex inside this blob is part of A and everything outside of this is part of B. So cutting a graph into two portions and splitting the vertices in two halves, two not halves, two partitions basically. It's just a partition. Okay. So in order to prove this, Prim's algorithm computes a spanning tree. We're going to do some building blocks. And the first of that building block is empty cut lemma. An empty cut lemma. What does this lemma say? A graph. So let me just, instead of writing it in words, let me just say it in words, so to speak. Okay. So what am I trying to do with this empty cut lemma? Well, all I'm trying to say is that a graph is connected if there exists no empty cut lemma, and if there exists no empty cut, then the graph is not connected basically. Then the graph is connected, sorry. So graph connected, no empty cut basically. And I think it's a reasonable, and it's very intuitive. It's a very reasonable and intuitive thing to say, because if the graph is connected, then whatever cut I choose, there will always be a path from the left hand side to the right hand side, because every vertex on the left hand side is connected to every vertex on the right hand side. So there exists no cut which is empty. And conversely, if we choose an empty cut, if a graph has empty cut, that means there exists a path, there exists no path from some vertex in the right hand side to some vertex on the left hand side. Basically, the graph is disconnected, or so to speak. So if I have a graph, let's say like this, and let's say it's a connected graph, that means there are edges between each pair of vertices. And if I cut it like this, then there is always going to be that one edge which crosses this cut, because every vertex on the left hand side has to be connected to every vertex on the right hand side. So there must exist some edge which is crossing the cut. And conversely, if there is an empty cut, that is, there are no edges crossing this boundary, that means this vertex A is not connected to this vertex B. So these 2 points are not connected. So it's a very, hand wavy proof, but it's simple. I think it's reasonable. And if you were to put it out in formal words, I think this is how you will do it as well. Next building block, double crossing lemma. So what this says is that whatever cut I choose, for example, whatever cut I choose, and if there exists a cycle in this graph and one edge of the cycle crosses this cut, then there must exist another edge that is also crossing this cut. And so the point is, only then will a cycle be complete. So double crossing lemma is, for every cycle, if there is existing one edge which crosses the cut, there must be another edge that is crossing the cut too. So let me put it in words. Suppose cycle C is belonging to the edges, has an edge crossing, has an edge crossing this cut, right? Then there is another, there is, this implies there is another edge crossing this cut, for this particular cycle. And a corollary to this is a lonely cut thing. So let me write that. I think that's the one which is the that is more important. Lonely cut. This means that for every cut, if there is only one cycle, only one edge crossing that cut, then that edge cannot be part of a cycle. Because if it were a part of a cycle, there would have been another edge crossing that cut, but there is only one edge crossing that cut. So if E is the only edge crossing a cut, then E cannot be in a cycle from the double crossing lemma from the. So here we go. Proof that Prim's algorithm returns a spanning tree. Part 1. After we have completed our building blocks, here we go. Part 1. That the Prim's algorithm returns a spanning tree. How do we look? How do we look? So is Prim's algorithm correct? That's the goal of this video. So first part is Prim's algorithm computes a spanning tree. That's what we are doing on the right hand side. To do that, we have made two building blocks, then empty cut lemma and a double crossing lemma, and now we're going to get to it. So the algorithm maintains an invariant that this set of T, whichever we are including in the algorithm, spans the set of vertices which have been included so far. And we cannot get stuck with x not equal to v, because that's how the algorithm is by design. And if it was ever a case that x is not equal to v, then that means there is a partition in the graph that such that the whichever vertices we have chosen are x and the leftover vertices are v minus x, and the algorithm is unable to find one edge between these two partitions. And that means that for this cut, there is no edge between x and v minus x, and hence the graph is disconnected, which is not true. So this can never happen. In other words, at every point of time, there will always be an edge from the x, that is vertices we have so far, and the vertices that are left. And we can always compute a minimum of such an edge because there will always be one, at least one. We can always compute the minimum of such an edge and we can include it in our t. We can include that in our t. So here's the statement. Here's the bigger statement. No cycles ever created in T. There will be no cycles ever created in T. Why? Okay, let's see. At any iteration of the algorithm, there is sets x and t. Okay? X are the number of vertices so far, and t are the number of edges so far included in our spanning tree. T spans x, and t is a spanning tree of x basically. These two sets at every time point, let's say t equal to t1, we have an x set and we have a t set where t spans x. None of the edges in T cross this cut because T spans X. So none of the edges, no edges in T cross X and V minus X, this particular cut. Because the T is only contained in the X. T has nothing. T has no regards whatsoever with V minus X. So no edges in T ever cross x and v minus x, this particular boundary. So whenever an edge e is added into particular t in the next iteration, let's say t1 plus 1 seconds, an edge e is added, right? This edge e is added to our set t. This could not have been at all in any possible cycle. This cannot contribute to any cycle in T. Why? Because if it were to contribute to a cycle in T, there would have been another edge in T which would have crossed the cut from the double crossing lemma. Right? Let's think about it. So whenever this edge E is included, so let's do it with some diagrams. Let's say this is our graph we have spanned so far, and here are the edges, and none of these. This is a spanning tree and this is not now. And for example, there are some edges crossing this cut, whatever, and let's say whatever number of edges based on the number of vertices in this graph. None of these edges can contribute to a cycle formation in X. Why? Because if it were to create a cycle in X, there would have been another edge crossing X and V minus X. And that's not possible because the only edges in X are the ones spanning this particular tree. So we are only building our graph edge by edge, right? We are only taking one edge at a time. For example, I can get confused in thinking such a way that there must exist an edge between this one and this one and this one and this one and this one, right? So there are edges which are crossing x and b minus x and are also part of this, but no, we are talking about the set t. So for example, initially this is how our graph behaves. This is it. There are no edges between any two. We are building the graph one edge at a time. So for example, first edge, I take this vertex, and first edge I choose this edge. Then I choose this edge. Then I choose this edge. Then I choose this edge. And then I choose this edge. And then I choose this edge. This is how our graph is going on at a time. Now, if you look at T, there is no way this any edge of T is crossing this particular cut. And hence, there is no edge of T which can result in generating cycles in T itself. So because we are building our graph one edge at a time, let's say we started with an empty graph and then we are placing edges one at a time in their particular places based on this greedy criteria. This is how we are going to generate our graph, and this is how we can rationalize this from the double crossing lemma. So if any edge were to be added, because that edge is going from the left hand side to the right hand side of the graph, and all edges in the left hand side are contained in the left hand side, there can be no way that any edge added will ever create a cycle. So as x goes on and on, as there are no cycles ever created, it will always return a spanning tree. See, because it's never possible that x is not equal to v. That means x at time t equal to, in let's say end time t equal to end time, x will be all vertices in the graph, and x will have no cycles because no cycle was ever created. Will have no cycles because none of them were ever created in this graph. So that means that this will have x and t will be a spanning tree, at least spanning tree. Now we will look at part 2, that this particular t is the minimum spanning tree. Okay.